What if I told you that we just witnessed a cosmic light show from the very heart of our galaxy? A fleeting 40-minute flash of light, erupting from the supermassive black hole that lies at the center of the Milky Way. This isn't science fiction. It's a groundbreaking discovery made by the James Webb Space Telescope, and it's completely changing how we understand these cosmic monsters. For the very first time, we've seen a flare from our galaxy's black hole, Sagittarius A*, in a new kind of light. This observation pierces through the veil of dust and gas that has long hidden the galactic center from our view, giving us an unprecedented look at the chaotic and powerful processes happening right in our own cosmic backyard. What caused this sudden burst of energy? What secrets does it hold about the engine that drives our galaxy? Today, we're diving deep into this incredible new finding, exploring the violent mechanics of a supermassive black hole and what it means for the future of astronomy. For decades, astronomers have stared into the heart of the Milky Way, trying to decipher the mysteries of Sagittarius A*. This black hole, with a mass of over 4 million suns, is relatively quiet compared to others in the universe, but it's not completely dormant. We've seen it flicker and flare in radio waves and X-rays before, but those observations only told part of the story. The galactic center is a messy place, shrouded in thick clouds of cosmic dust and gas that block most kinds of light. Imagine trying to watch a fireworks display through a dense fog. You might see a few bright flashes, but you'd miss all the intricate details. That's the challenge astronomers have faced. But now, we have the James Webb Space Telescope, or JWST, and its powerful mid-infrared instrument, MIRI. Mid-infrared light is special. It has a longer wavelength than visible light, allowing it to cut right through that cosmic fog, giving us a clear, unobstructed view. And what a view it was. On April 6, 2024, a team of astronomers pointed JWST at Sagittarius A*, and they caught something incredible. A flare. A sudden brightening that lasted for about 40 minutes. This was the first time a flare from this black hole had ever been seen in mid-infrared light. The team, led by Sebastiano von Fellenberg, could track the flare's brightness as it peaked and then faded away. This new data is like a Rosetta Stone for black hole physics. It allows us to connect the dots between what we see in different parts of the electromagnetic spectrum. For years, we've detected variability in radio waves coming from the area around the black hole. Now, with this mid-infrared flare, researchers believe they've found a direct link. It seems the same group of superenergetic particles is responsible for both emissions. By observing in this new light, we're not just seeing the flare itself, we're seeing the engine behind it. So, what could possibly unleash such a powerful burst of energy from the edge of a black hole? The leading theory sounds like something out of a superhero movie: magnetic reconnection. Picture the region around Sagittarius A** as a tangled web of incredibly powerful magnetic field lines. These fields are constantly being twisted and stretched by the black hole as immense gravity and the swirling disk of hot gas around it. Magnetic reconnection happens when these tangled lines suddenly snap and then reconnect in a new, simpler configuration. This process releases a colossal amount of stored energy in a very short time, like a stretched rubber band snapping. This energy blast accelerates nearby particles, specifically electrons, to nearly the speed of light. These superfast electrons then spiral along the remaining magnetic field lines, emitting radiation as they go. This radiation is what we observe as a flare. The new JWST data strongly supports this idea. The way the flare's brightness changed over time fits perfectly with models of magnetic reconnection. It's a much cleaner explanation than other theories, like random turbulence in the gas, which would likely produce more sporadic and unpredictable bursts. The connection to the radio wave observations is also a key piece of the puzzle. It suggests that the same population of hyperaccelerated electrons is producing both the mid-infrared light and the longer wavelength radio light we see. This gives scientists a powerful tool to probe the physical conditions right at the event horizon. Based on their models, the research team estimates the magnetic fields in the flaring region are somewhere between 40 and 70 Gauss. To put that in perspective, that's up to 140 times stronger than the Earth's magnetic field at its surface. It's these intense fields that act as a cosmic particle accelerator, creating the light show we just witnessed from 27,000 light-years away. One of the most exciting details from this observation is the timing. Astronomers have previously seen similar flares in radio wavelengths using telescopes like the submillimeter array. When they compared the data, they found something fascinating. The mid-infrared flare detected by JWST appeared to happen about 10 minutes before the corresponding flare in the radio data. This delay is a crucial clue. It tells us about the journey of the energy being released. The mid-infrared light, having a shorter wavelength, is likely produced right at the site of the magnetic reconnection event, where the electrons are at their highest energy. As these electrons travel outwards and cool down, They lose energy and start emitting light at longer and longer wavelengths, eventually producing the radio waves we detect later. This 10-minute delay is essentially the light travel time and cooling time of the particles. It allows us to map the flow of energy away from the black hole in real time. Think of it like watching a distant lightning strike. You see the flash of light almost instantly, but you hear the thunder a few seconds later, because sound travels slower. In this case, both signals are light, but they represent different energy states of the same particles. The mid-infrared is the flash, and the radio wave is the thunder that follows. This gives us a way to study how particles cool down in one of the most extreme environments in the universe. As the flare fades, JWST can track how the spectrum of light changes, shifting to longer wavelengths. This directly confirms our models of how electrons lose energy as they radiate. The big question now is whether this 10-minute delay is a consistent feature of every flare, or if it changes depending on the size and location of the event. Answering that will require many more coordinated observations between JWST and radio telescopes around the world. This single observation has thrown open a brand new window into the heart of our galaxy. The ability to see Sagittarius A* in the mid-infrared is just the beginning of a new era in black hole research. We've moved from simply knowing there's a black hole there, to actively watching the physics unfold around it. Every new flare we catch will add another piece to the puzzle. By combining infrared and radio data, we can create a multi-dimensional map of the environment around the black hole, tracing the flow of matter and energy with unprecedented detail. This helps us refine our models of accretion disks, the swirling vortex of material that feeds black holes, and understand how they power some of the most luminous objects in the universe, known as quasars. While Sagittarius A* is relatively calm, the physics at play is universal. The lessons we learn here can be applied to supermassive black holes in distant galaxies, helping us understand their much more dramatic and violent behavior. And the implications go even further. Supermassive black holes aren't just passive objects sitting at the center of galaxies. They are active engines that profoundly influence their surroundings. They play a critical role in what's known as galactic feedback. The immense energy and radiation blasting out from a black hole's vicinity can heat up or even blow away the gas in the galactic center. This can regulate or even shut down star formation in the area, shaping the evolution of the entire galaxy over billions of years. How does this feedback mechanism actually work? How do black holes influence the structure of their host galaxies, the flow of gas, and the birth of stars? These are some of the biggest unanswered questions in astrophysics. With the power of JWST and future infrared telescopes, we are finally gathering the data needed to answer them. We're not just studying a black hole. We're studying the heartbeat of the Milky Way. This 40-minute flash of light was more than just a beautiful cosmic event. It was a message from the galactic core, and we are just now beginning to translate it. Thank you so much for joining me on this journey to the center of our galaxy. It's discoveries like this that remind us how much is still out there, waiting to be found. If you're as fascinated by the cosmos as I am, make sure to like this video and subscribe to the channel for more deep dives into the latest astronomical breakthroughs. What do you think is the most exciting part of this discovery? Let me know in the comments below. Until next time, keep looking up.